Yes, here. See that? So that field is called a receiver window. So this is the empty part of the receiver buffer, which can be used by the receiver to receive segments. That gets reported possibly in every segment. Okay? So the sender has the information. طيب, Bismillah ar-Rahim. So we'll continue our discussion for transport layer protocols. We covered the principles of reliable data transfer, and we started to talk about TCP. We talked about reliable data transfer in terms of general principles, and we talked about the different versions of reliable data transfer. We talked about the segment structure for TCP. We explained the function of each field in the header, and we also discussed the issue regarding the timeout and how critical calculating the timeout. And we went through the method that TCP uses to calculate the timeout based on some iterative approach. Today we'll talk about reliable data transfer for TCP, not principle, but we need to talk about reliable data transfer for TCP. So it can easily make sure not to overwhelm the receiver. So we need to ask ourselves, like for example, we discussed stop and wait, we discussed go back in, we discussed selective repeat. We talked about the differences between these approaches. So the question is now, does actually TCP use go back in? Does it actually use selective repeat? Okay, so that's what we need to answer. And the quick answer is it uses neither. So it uses sort of an approach which is mixed of both. So that's what we need to explain. Why this mixed of both? Because it tries to optimize the development of the protocol, okay, while trying to achieve the same efficiency of both protocols at the same time. So it tries to work on the good of both. So we'll see how TCP tries to achieve that. So TCP creates reliable data transfer service on top of IP. Why we highlight this here? Because keep in mind that IP is unreliable inherently. Okay, so designing a transport layer protocol on top of an inherently unreliable network layer protocol will be different, of course, right? So we know that IP is best effort. This is very important, and we'll see the impact of this on the design of TCP, drastic impact on the design of TCP. So definitely TCP uses pipeline segments or pipeline approach, similar to go back in and selective repeat. Both are pipeline, which means pipeline here, we mean that we don't have to send one segment at a time and wait for the acknowledge. So we have a window technique for sure. So we can send multiple packets without having to wait for acknowledgement. But even the N here is not specified. So we said that go back N and selective repeat, and we have a certain window. No, here is byte based, and there is no fixed N. So we'll see how this is done. So cumulative acknowledgement. Cumulative acknowledgement is one of the characteristics that we talked about for go back N, right? So does that mean that TCP is go back N? No. Okay, so we'll see why no. TCP uses single retransmission timer. Okay, so that actually confirms that it's go back in. No, it's not. It's not exactly go back in. It's not exactly go back in, because go back in does use one timer, right? We talked about this last time. For the entire window, we use only one timer, صح? And that's efficient. But the problem with the one timer per window, what was the problem? Remember?
When the packet gets lost.
Yes. What do? We retransmit the entire window. So we're not going to do this here. Okay, so this is the start of trying to have a differentiation for TCP. So retransmissions are triggered by, of course, normally by timeouts, right? Okay, but here TCP uses something a little bit different or additional, okay, which is called duplicate acts. Duplicate acts here, remember we talked about the possibility if you have a sender and a receiver, right? If you send, and I will not use byte, I will use indices here just to make it simple. So if you send the first segment 0, right, and send segment 1, and it's lost, right, and then send segment 2. So here, the receiver first will send acknowledgement for 0, acknowledgement for 0. For TCP, as we said, TCP uses the acknowledgement as 1 here. Why? Because it says that I received up to 0, okay, send me 1, or this is the expected one coming next, right? So if the receiver receives segment 1, it should send acknowledgement 2, right? But it didn't, right? Instead, it receives segment 2. So here, what do we say? What do we send in terms of acknowledgement? Huh? Yeah?
Last successfully.
Right, which is 1, exactly. Right? Because it expects everything in order. Assuming this is go back N. Okay? For selective repeat, right? It would actually use acknowledgement for all the received packets and accept accept the segment in the buffer. But TCP will not do that. TCP will send the acknowledgement for the last successfully received segment, right? So as you can see here, this is called duplicate ACK, right? Yeah. And if I send 3, okay, what the receiver will do will send a acknowledgement, 1. It will keep doing that. It will keep doing that until it receives segment 1. So all of these we call them a duplicate acts. These duplicate acts are very important because the sender takes these duplicate acts as a clear indication for something. Obviously that there is a segment that was lost, right? صح كده? Okay, so this is another indication that there is a segment that was lost. Okay? Different from the timeout. The timeout will also, of course, will clearly indicate that the segment was lost. تفضل.
The packets that was received unordered, will it queue it?
No. Here it doesn't. No. Here it doesn't. No, the receiver expects to receive the segments in order.
Okay, when it doesn't receive it and it sends the acknowledgement,
Yes.
what will it do with number 2?
ما هو we said that this is the workaround for not having to send negative acknowledgement. So instead of sending negative acknowledgement, we send acknowledgement for the last successfully received segment.
Yeah, this is understood, but what will it do with the 2 that already received not in order?
2, it will, here بقى, we'll see بقى. Will it accept it or not?
Yeah.
Believe it or not, بقى, the standard doesn't say. The standard doesn't say. It expects the reception to be ordered. But will this segment be accepted or not? Both are fine. Okay? We'll talk about this. ففهمنا, this is the slight difference between timeout and duplicate. Timeout is when I have the timer fires. Okay? And in that case, if this acknowledgement arrives here, then I will proceed to this, and the timer will restart here. Okay? So if the timer expires, then I go to the first segment and send all, if it's go back N, I would send all the segments, right? Again, okay? But actually TCP will not do that. This is also a differentiation between TCP and go back N, okay? So initially, consider simplified TCP sender, ignore duplicate acts. So we will try to analyze the performance of TCP by first ignoring the duplicate acts. If we ignore the duplicate acts, so the only indication for us to that there was a segment that was lost is the timeout. And ignore flow control and ignore congestion control. We'll start to simplify. We'll start to relax these assumptions, okay, and talk about the practical implementation of TCP. But this is the initial thing that we will keep in mind, but later on we will remove these assumptions and start talking about the practical TCP implementation. Yani maybe this one has arrived to the receiver, right? And I will receive the acknowledgement for it later. So this is part of trying to make TCP efficient compared to go back N, to try to avoid retransmitting the entire window. So we're not going to do this. We'll only retransmit the first segment only, okay? Here, I did not receive acknowledgement 1. And here, this arrived. And the acknowledgement here would be 2, right? And I received the acknowledgement 2, but I did not receive acknowledgement 1, right? What does this indicate to you? That both 0 and 1 have arrived. So acknowledgement 2 would indicate that I received everything before it correctly. واضح? What it does, طيب. So the sender, as we said before, the sender has three types of events, right? It has segments coming from the application, okay? Acknowledgement come from the network, and what? There is an internal event, right, which is timeout. So these are the three possible events that we have. So there is data received from the application. So when the data is received from the application, what we will do is that create segment and report the sequence number. When we create a segment, معناها we update the header. And the header, the minimum thing is that we put the port number, the sender port, the receiver port, and the sequence number. This must be there, okay? The sequence number is byte stream, as we said before, okay? So the first segment will start with a sequence number of 100, doesn't have to start from 0, okay? And depending on the length of the segment, if it's like 200, then the next segment will start with a sequence number of 300. So the first one is 100 and the length is 200, so the sequence number of the next segment will be 300, and then 500, and then 700, and so on, okay? So the sequence number reports the byte stream. Start timer if it's not already running. So when I send the first packet, it's like here it's similar to go back N. So when I start sending the first segment, I will start a timer. So the timer indicates that I should receive an acknowledgement before this timeout fires, okay? And then I will set that timer with the timeout interval. Okay, if there is a timeout, retransmit only the segment that caused the timeout. This is a clear difference. So go back in would do what? Would do everything. No, TCP will only send one segment. Only one segment, the one that caused the timer to. So for this, it's actually similar to selective repeat, not similar to go back in. Okay? And what that implies here is that, I don't know, maybe. So that's why I said that TCP is actually a mix of both the go back in and selective repeat. Okay? Type. The other event is if an acknowledgement was received, if acknowledges previously an unacknowledged segment, then update what is known to be which indicates here is that acknowledgements are cumulative. So if I don't receive, so for example, so this indicates that acknowledgements are cumulative. Okay, so even if one or two of these acknowledgements were lost, okay, I can still have no effect whatsoever. Okay, type start timer if there are outstanding signals. That makes sense. So that's these are some scenarios that gives you some indication about how TCP can work. As we said, that timeout is one of the very critical parameters that it has like some trade-off. If it's too long, will not utilize their channel efficiently, like this scenario here. So if the timeout is long, and I have to wait for the acknowledgement for each packet or each segment before I send the other one, then the channel utilization will go down, right? So, for example, for this segment, the acknowledgement was lost, okay? Assuming that this is assuming that this is stop and wait. So TCP, as we will see, when it starts at time 0, it initiates itself as a stop and wait. Okay? And then later on, it starts to increment. We'll see that. We'll see that after a few minutes. Okay? But TCP, it may actually start as initially stop and wait. So if the acknowledgement here was lost, timeout will expire, and I will send. The problem with this scenario is that the channel utilization is very low. Okay? But I was able to deal with this. There's no issue. And only when I receive the acknowledgement, I increase the send base. So here, I have sequence number is 92, and the segment size is 8, right? So that's why the send base here is a 92 plus 8, which is 100. واضح كده صح? So that's fine. Later on, if I receive that acknowledgement, TCP would feel, oh, okay, let me send 2 packets and see what happens. That's practically how it does. Okay? So I will send 1 segment, okay, fire the timeout, but I will not wait. I will send the other segment. تفضل. Diamond doubles. Okay? We'll see why. We'll see why it does that. Okay? But for now, let's talk about these scenarios independent. So assume it works as a stop and wait. And after this, it sends two segments. Okay? Here, the issue is that I have a premature timeout. So we're trying to see, what we're trying to say here is that if I have go back in, I would, here, when it times out, what will I do? I will send both segments again, right? But TCP will not do this. TCP will only send one, the first one, right? So the issue is here, when the receiver receives this one, right? This one has been received before. So it will send an acknowledgement for the last successfully received segment, right? Which for the sender is cumulative acknowledgement. So I don't have to send the other one. See how we avoided the scenario of go back in? Okay? So here, we used one timer, and we didn't have to retransmit all the segments in the window, similar to go back in. Okay? So we used like some kind of a mixed approach. واضح السيناريو هنا؟ Okay? So that happened because of a delayed acknowledgement. Okay? So this delayed acknowledgement is mitigated very efficiently. But of course, if I did not receive the acknowledgement at all, that's different. Okay? That's different. In that case, if I receive this acknowledgement, again, cumulative, خلاص عادي, I will accept both. ما فيش مشكلة. إنما if the acknowledgement is lost altogether, then I have to retransmit both. أنا ما عنديش option تاني. I have no other option. Okay? Here, I have the two segments. One segment was lost and the other one was received. In that case, again, this is a cumulative acknowledgement, so that nothing is actually new here. So even if the timeout is long enough, so I was able here to receive both of them, even if the timeout is long or the timeout is premature. In both cases, TCP was able to recover both segments using one acknowledgement only. طيب, هو بقى the question is now, how does the receiver generate this acknowledgement? Okay, so one approach is to say that, one simple approach, we say that send, receive. Remember, the acknowledgement is cumulative, right? So the sender sends the segment, I will send acknowledgement, right? Sender sends another, I will send acknowledgement. So the receiver in that case is dumb receiver. Whenever it receives a segment, it sends the acknowledgement. But if these two segments arrive here in very short time, right? What is the point of sending two acts? I can send one for both of them, صح? That's also part of trying to be efficient, right? But the issue is the receiver doesn't know when it will receive the second segment. Okay? So what is the approach بقى هنا to send the acknowledgement? That's what this slide tries to answer. So what we will do is that we will say, so the receiver will say, arrival of in-order segment. So this is the segment that I'm expecting. Everything is in order. Yani, things are fine. So all data up to expected sequence number needs to be acknowledged, right? So I need to send the acknowledgement. However, the receiver will wait for short amount of time, which is 500 milliseconds. هتقول لي اشمعنى 500 milliseconds? Again, nobody knows. This is similar to alpha is 0.125 and beta is 0.25 and this dev RTT is 4 multiplied by 4. All of these are empirical parameters. Okay? Type. So the receiver will wait for 500 milliseconds. If it receives another segment within that time only, it will send the acknowledgement for both. So it sends one for both, for two only, right? If it waits for 500 milliseconds and it does not receive a segment, it will send acknowledgement for the first one that was received. Okay? So this is only trying to be a little bit efficient using the property of cumulative acknowledgement. So arrival of in-order segment with expected sequence number, one other segment has pending, right? So what this tries to say is that I received the segment, I will wait for maximum 500 milliseconds, okay? After 200 milliseconds, I received another one. I don't have to wait, خلاص. Because there is another segment pending. So it's only two, okay? So again, at the timeline, this is how it looks like. So the receiver receives the first segment. So before it sends an ACK, it will say, okay, so I will wait for 500 milliseconds, okay? And then I received here, after 200 milliseconds, I received. In that case, I don't have to wait, خلاص. Send the acknowledgement. Okay, I don't have to wait. If the sequence number here equals to, let's say, 93, what is the acknowledgement number here? 94 بالضبط, برافو عليك. واضح كده؟ Okay? If this is, let's say, if this is 83 mesh, okay? If this one was delayed and came after 500 milliseconds, so in that case here, I will send the acknowledgement with 84. Okay? And it's only 2. Okay, so I will not have to wait within 500 milliseconds to receive 3 or 4. No. Once I receive the second one, I will send the acknowledgement. So it's either 1 or 2. That's it. واضح كده؟ طيب. The question بقى is arrival of out of order. Out of order. Higher than the expected. So which means that here, 93 did not arrive. And now it's 103. This one arrived. Okay? And it's within the 500 milliseconds. What do I have to do? We know. We will have to send a duplicate ACK. Duplicate ACK. Okay? Here, this is the answer to your question. What happens if I have arrival of segment that partially or completely fills a gap? Which means that here, I received this segment, and this segment was not actually lost, but it was delayed. I received another segment after that, okay? So here, I will have to send duplicate ACK. We know that. But after some time, I received this one. It's just that it was delayed, not lost, right? واضحة دي, yeah? So after some time, I received a segment that fills a gap. Okay? Okay. Here, it depends. It depends. And this touches on the question that you posed earlier. Did I actually accept this one in the buffer or not? Okay? Because if I had accepted this one, then the acknowledgement that I should do next is actually the acknowledgement for all of them. Right? If I did not accept this one before, then the acknowledgement will be only for these two. Type, does TCP force the receiver to accept or not? The standard does not force this. So it's up to the implement. That's why there are multiple RFCs. So some RFC, they report that the receiver should accept the out-of-order segments in the buffer. Okay? In all cases, we fire duplicate ACK, remember. We fire duplicate ACK. But the acceptance is another thing. We accept the segment in the buffer, but we never, ever send it up to the application, right? Because it's out of order. Okay? So accept it in the buffer, or not accept it, it's up to you. Okay? But send it to the application, never. Okay? And in both cases, we send duplicate ACK. The idea by here is that if we receive a segment that fills a gap, okay, then we send cumulative acknowledgement. So these cases are clear. Any sequence here or any of these cases is not clear, let me know. Okay, so these are the 4 cases that the receiver has. No other case.
When we say I'm sending an acknowledgement for the 3, how?
Then a sequence number. So assume this, this is 0, 1, 2. So what is the acknowledgement here? Huh? Yes. So if this one had been accepted, then this acknowledgement will be 3. If this one has not been accepted, then this will be 2. Okay? Both implementations comply with the standard. The standard does not dictate this part. Okay?
We can send ACK3 without receiving the first segment, the sequence number 1.
No. The scenario that we're talking about here is that I received first 0 and then 2, okay? And then in a later stage, I received 1. Okay? In a later stage, I received 1. Within the there is no timeout at the receiver, remember. But within the 500 millisecond, yes, within the 500 millisecond. طيب. The question is, someone might say, okay, so TCP is connection oriented, right? صح? Connection oriented, it should by default guarantee the order of the packet. Will it? No. Connection oriented is different from circuit switching. Eh? We talked about circuit switching. This is at the physical topology. Connection oriented at the TCP level is logical, it's not physical. So I will explain this visually. So here I have the sender and I have the receiver. In between, there is network of router and switches. Okay? So here I have an application at the transport layer, right? And transport layer protocols, they facilitate the end application to end application communication, right? In bidirectional. So here, the sender will send segment 0, and then segment 1, and then segment 2. Okay? Will they arrive in the same sequence? No. Even if they are connection-oriented? Yes. Why? Because the fact that TCP is connection-oriented, it doesn't mean that each packet or each segment will take the same routes in the network. Why? Because IP does that. And we don't control how IP works. In fact, IP is best effort. In fact, some of these segments might wander around in the network for years before they arrive. Even if the transport layer protocol is connection-oriented, yes.
So what do we mean when we say connection-oriented?
Connection-oriented means that I have to establish a connection before we start communicating, okay? For circuit switching, we've been telling you that circuit switching does that. But you have to establish physical circuit.
It's the conversion pair because these two are on 2 layers, so...
صح, true. But exactly, that's why I'm trying to give you the difference. When we talk about circuit switching and we say that circuit switching is actually, it tries to establish a circuit before communication, what we mean here is a physical circuit. When you establish a pipe, physical circuit, you are quite sure that things will be in order. But here, it's not a pipe, it's not a physical, right? It's not physical, so it's an end-to-end. In between, there could be hundreds of routers. So it's just a logical thing. When we say that connection here is a logical thing, it's not physical. So when TCP tries to send the segments are sent independently inside the network. It's exactly like this. I have caravan of cars, and I tell them, okay, so I will go to Khor and meet you there, right? But I did not give them a restriction that they should follow certain route. That's exactly what happens, okay? But you have to arrive at the other side, okay? So each one of them will be free to take different streets and different routes. Some of them might arrive later than the others, right? So they may not arrive in order. So that's exactly what happens here. And that's because TCP, and this is one of the fundamental issues for any transport layer protocol, we don't have access to network. We don't know how the network will behave. So for us, the network is sort of a black box. And it's by design because layers are isolated, right? But that has implications. And I should design the protocol based on that. So that's one of the issues, that the fact that this segment did not arrive before this segment, it doesn't mean that it was lost. We've been assuming that it was lost. And we send duplicate ACK as if it was lost, but it may not have been lost. And it may arrive in a later stage.
Don't we have routing tables
Right?
to like at least
Yes.
try to solve the issue?
Yes, but there is no guarantee that these segments will go through the same router أصلا. There's no guarantee. Okay, let's think from the situation of the IP. You have segments coming, okay? The routing table based on the IP of the destination might send it to some forwarding routers, right? Does that guarantee that all these segments will have to follow the same route? There's no such guarantee, because IP never promised that. Because IP, what it promises is a best effort. Best effort, right? Some of them might get into a router that is jammed and it has to wait. Some of them might have clear path and it goes all the way. We'll talk about traffic jams in a later stage. That's another thing, don't get us into this, because yes, don't get us into this. Yes, cross layer. What I'm saying actually was a motivation for some people to try to get into cross layer, but cross layer complicates things drastically, and we'll talk about one of the issues here. But cross layer is another issue. Okay, for us here, we follow layer isolation. So for us, for TCP, IP is just a black box. The network is just a black box. Okay, but this is one of the implications. Okay, طيب. We've been saying that for retransmission we have to wait for timeout, right? When the timeout expires, we will retransmit. And for go back N, we used to retransmit the entire window, but actually TCP will retransmit only the first segment. Okay, and wait for the acknowledgement. Okay. Another indication for lost segments is what we call the fast retransmission. So what happens is, this will touch on the same scenario again. So this is the sender and this is the receiver. So the sender here sends segment 0. I will try to use indices, not bytes, just for simplicity. So segment 0. Segment 1, still wandering in the network, but segment 2 arrives. Okay, if it's within the 500 millisecond, then here I can send acknowledgement 1 بالضبط. Okay, so here I can send acknowledgement 1 as well, right? So this is called the first duplicate act. The first duplicate act, right? Type. Then segment 1 still, this guy seems to be a little bit less intelligent, so he's going to al-khor through رأس رجاء الصالح, he's lost, ماشي? But segment 3 has arrived. Arrived. Okay? So here I send a 1. صح? Okay? Segment 1 still did not arrive. So here 4 1. Okay? So these are 3 duplicate acts. All of these happened before the timeout expire. Okay? If the timeout expires, then that's fine. We know what to do. We will send 1. Okay? But the 3 duplicate acts are indications that this segment may never come. Okay? And you don't have to wait for it, because it looks like it's lost. Okay? A very common scenario for this is packet circulation in the network. Again, this is rerouted in a wrong way, so it keeps circulating in the network. Okay? So it may never arrive. May never arrive. But there is still 0.1% it will arrive after 1 hour. We don't know. But for us, this is called a fast retransmission. So here, the sender receives these duplicate acts, 3. Okay? So if the sender receives 3 duplicate acts, even if the timeout did not expire, I will take this as an indication that no, I have to go back and send this segment regardless. So why do I do this? Because maybe the calculation of the timeouts that I have at the moment is longer than usual, so I don't have to wait for the entire timeout. So I can just do a fast retransmission. So this is what is referred to here as fast retransmission. So fast retransmission for TCP is indicated by 3 duplicate acts received at the sender. Okay, in that case, I don't have to wait for the timeout to fire up. I will have to send the segment regardless.
When you say I will have to send the segment regardless,
Mm-hmm.
the full one, or what do you mean?
1. ما خدي بالك لو يعني here acknowledgement 1 has arrived, which means that the send base will go here and the timer will restart. Okay? So I always restart from the one that has not been acknowledged before. If it was acknowledged, then خلاص. خلاص. ماشي? So this is what we refer to as fast retransmission. So resend the segment without having to wait for the timeout. This is indicated by 3 duplicate acts. Okay. واضح كده؟ This illustrates that scenario. So here, remember here, I will advance the send base and a restart timer. That's what the sender does. For me, this is the first acknowledgement. It's not a duplicate act here. This is this is acknowledgement for the last successfully received packet by the receiver. Okay? So let's put some numbers. So here this is 0, this is 1, this is 2, this is 3, this is 4. What is the acknowledgement here? 1. So this is the first acknowledgement I receive with an index of 1. It's not a duplicate act, right? But because segment 1 did not arrive to the receiver, this acknowledgement will still have a 1. So this is the first duplicate act. This is the first one. Okay? Here, 1. And here, 1. So these are 3 duplicate acts. So I don't have to wait for the timeout in that case. I can just resend segment this one. In our case, this is 1, by the way. Lay a second segment, which has a sequence number of 1. Okay, so that's easy. So this is the code. Yeah, this is the pseudocode that corresponds to what we just explained. Acknowledgement received was the acknowledgement field value of y. If y is over the send base, so this is what I'm expecting. So that's a normal acknowledgement. So in that case, there are currently not yet acknowledgement segments. So I will accept this acknowledgement. This is the first one. It's not a duplicate act. This is the first one. I will restart the timer. Okay, and then else, if it's an index that's equal to the send base or less, then we have to increment the duplicate act count. If that duplicate act reaches to 3, then we على طول engage in retransmission. So this is a rollback of what we just said. So that's the reliable data transfer for TCP. I hope now you have the whole idea that it's really a mix of both. It's not go back and it's not selective repeat. It's actually a mix of both. It tries to use the advantages of both at the same time. When it comes to flow control is the easiest part in TCP. We said that the definition of flow control is what? We try to
Over 1 per
We try to avoid, يعني. We try to avoid so what do we do to avoid this? We need to regulate the transmission rate. That's easy. Because the sender and the receiver, they have full visibility to each other, flow control in that case is very easy. Okay? Because the sender and the receiver, they have visibility to each other, right? Do we have another scenario? Yes, we'll talk about congestion control. When we talk about congestion control, it will be clear. So the receiver side has a buffer, and I'm trying to avoid overwhelming that buffer. So the receiver side is the socket at the receiver, and we have access to the empty part of the buffer. This is what we refer to as the receive window, which is reported by the receiver to the sender as part of the protocol. Remember, we talked about. Okay. So what it does here is that it needs to calculate this and put it in a segment while it sends an acknowledgement to the sender. Okay? And the sender will say, okay, so I have this receiver window. I cannot send segments more than this empty buffer in the receiver. That's easy. Okay? So the way we do this is by calculating what we call the receiver, the buffer size minus the last byte received and the last byte read. اللي this and this. So this, because we said that this is byte stream, so it's a byte stream. So this is the last byte read and the last byte received. So I subtract this receiver buffer size from this. I get the empty buffer. And this empty buffer, I put it as part of the acknowledgement back to the sender. And I always report that. So the sender easily can try to avoid sending more than this buffer. So if it tries to send and it exceeds that buffer, then it stops. Okay? That's why we said n is not limited. So when we talk about go back n, n was fixed. We don't have to fix it here. So n is in fact implicitly controlled through flow control. So we can keep sending. If the receiver tells you that I still have a buffer, theoretically we'll keep sending. So n can potentially grow large. Okay? To what extent? أيوة الله ينور عليك. That's what I wanted to hear. Okay, so there is another constraint. So we can have a scenario where we don't overwhelm the receiver, but we overwhelm the so that part is very tricky. It's not as easy as flow control. Because we said congestion control is to also try to regulate the sender transmission rate, but to avoid overwhelming that network in that case. You are jumping ahead. خلينا بس هو because there are two scenarios, reactive and proactive. We'll talk on explicit and implicit. We'll talk about this. There are different types. Okay? The difference here for the congestion control is that the main difference is that TCP does not have visibility to the network. We have visibility to the receiver, right? Because we are in the same layer, and I know the buffer size at the receiver, and I can control easily the transmission rate based on the receiver based on the receiver buffer. But the network, I don't know. It's like a highway, okay? I can insert something in the beginning of the highway and receive something at the end of the highway. Okay? But I don't know that this highway has different exits and entrances, right, in the middle. I don't see that, right? I don't see this. So I can get some cars in the entry point of the highway and pray that this will not get to a traffic jam in the middle. I don't know, right? So even though we have no complete visibility in the network, we need to regulate the transmission rate at the sender to try to avoid that, okay? So here, the question is, how can we have some information about the congestion or the possibility of having congestion? This is the big question. This is the big question. So congestion is formally or informally defined as too many sources are sending too much data fast for the network. This is the scenario that I just talked about. So if you have a sender and a receiver, okay, who are sending to each other segments, right? So these send and receive, however, they don't really have access to other sources of segments that come to the network at the same time, right? I don't have any visibility to these. Okay? So I send, but I don't know if and when the congestion will happen in the middle. And I don't have actually clear visibility to this. So this may happen through some, remember, just the fact that a segment was lost or delayed, okay? Is that an indication of a congestion? Maybe yes, maybe no. We don't know. We don't know. We cannot really tell. Okay? If many segments have been lost completely, okay, that might be an indication that one router here has like buffer overflow and it keeps dropping the packets. مثلا. That's maybe a clearer indication that there is a segment, there is a congestion. But one segment is lost. Is that necessarily an indication of congestion? We don't really know. We don't really know. Okay? So that's why congestion control is one of the top 10 problems. Similar to مثلا internet scalability, resource optimization in a network, or something like this. Video content management on the these are grand challenges. They say these are grand challenges when we talk about networking systems. No one has optimal solutions for eliminating these problems. They will never vanish from our real life. There will always be a problem. So congestion control is also one of these grand challenges because of the fact that TCP does not have full visibility to the network. If we don't have full visibility to the network, we have to make certain assumptions. Okay? Type. So the way we will approach congestion control, similar to reliable data transfer, but the difference here, we're not going to use finite state machine. Here, we'll talk about the principles of congestion control to start to get motivated and appreciate why congestion control is actually a big, huge issue for any transport layer protocol. Okay? So we'll talk about the principles, again, making certain assumptions, okay, and try to relax these assumptions step by step to get more and more into a practical case. So the first case here is very, very, very simple. Very, very simple. So we have only two applications sending to a shared router. Okay? Type. That's one. Of course, in real life, it's not just a single router. It's many, many routers and end-to-end communication and so on. But here, let's think about the simplest scenario. So we have two applications, right? Sharing the bandwidth of the router. Not only that, the buffer inside the router is infinite. Which means that we will never miss any segment. Segment can be delayed, but not lost. There's no way it can be lost. Okay? So we know we want to try to model this, to model the performance of this. So the transport layer here can increase the rate of transmission. Up to when? We know that assuming that the transport layer protocol is fair and both applications are increasing their transmission, right? And here the capacity of, or يعني the service rate of that router is C. What is the achieved throughput for each of these two applications? لا, they are sharing the same router, C over 2, right? So we can model the transmission rate from the transport layer to lambda in, which is what the application is actually sending to the transport layer, right? And all these segments will go through to the network with no segment loss whatsoever, which means that the transport layer will never have to retransmit anything. صح? We will never have to retransmit anything. Okay? So we will always assume that these segments will arrive at the receiver side. Okay? So the question is, how lambda out evolve over time given that we increase the rate of transmission from the sender? Okay? As long as each of these applications does not reach C over 2 as transmission rate, actually lambda in, lambda out equals to lambda in. صح? We know that, assuming that the transport layer protocol is fair. Okay? Which means that they will share the router capacity, and on average here, I will have one segment from each. Okay? And nothing will be lost, so lambda out equals to lambda in. Okay? But here, I will never have a rate over C over 2 for any of them. Never. صح? So lambda out cannot exceed C over 2. Okay? واضح, ده logical. Okay? طيب. This is the throughput or lambda out, or what we call يعني for accuracy we call it good put. Good put معناها ايه؟ The effective data that reaches the application on the other side. Okay? So it cannot exceed C over 2. So what about the delay? The delay here, if you are less than C over 2 transmission, okay, chances are the queue length will be a little bit small, which means that whatever comes, it will not have a significant delay. It will go out. But once you reach, you approach the capacity of the router will start to fill the buffer very, very, very long, right? So the critical part of the delay here will be the queuing delay. صح? As the router builds up in the buffer, the queuing delay will start to increase exponentially. صح كده? It's exactly similar to, this is congestion, so we're getting into the bank, and the teller is a little bit lazy, right? So people will start to come, line up, and all of a sudden we see infinite line of people, and the teller is not able to cope with this, so everyone will have to wait for a huge amount of time to get his or her service. So the queuing delay will grow exponentially. Okay? Make sense? Okay. طيب. So that's very simple scenario that shows the effect of congestion in a very, very simple scenario. But still, يعني, we can live with that. يعني, if lambda out grows until C over 2 and then it keeps itself fixed, we can live with that. There is no serious issue so far. طيب هنا بقى the router has finite buffer size. What is the difference here? Finite buffer size. If actually lambda n starts to grow, right? After some time, the router will get filled, and the router will have to drop the segments. What is the implication of this? The implication here is that the transport layer will have to retransmit the segment. صح? We know that. And here we have to retransmit. تفضل. Finite buffer here means that the buffer size is limited. It's not infinite. الثاني كان infinite. Here it's finite, which means it's limited. So here the segment will be dropped, right? So if the segments are dropped, it's fine. We have designed our transport layer protocol to deal with that. The transport layer protocol will do what? Retransmission. صح? Okay? Which means that the transport layer protocol will have another rate of transmission, which is slightly over the application rate of transmission. Is that understood? Why? Because here, the transport layer protocol will have to send all the transmitted segments from the application plus the retransmitted segments. صح? So here, lambda n dash equals to lambda n plus retransmitted segments. صح? So here lambda n dash in general is greater than or equal to lambda n. صح كده؟ طيب. Here by the constraints is on lambda n dash ده بقى. This lambda n dash should not exceed C over 2. Right? So, which means that lambda n will almost never touch C over 2 أصلا. Will always be less. Okay? So that's that scenario. So because of this limited buffer, we cannot reach lambda over 2 except if we start pushing hard, we can get lambda out يعني very, very close to C over 2. Okay? So the sender here sends only when the router here بقى this case is slightly different. So this case, by the way, is divided into 3 cases. Okay, just to make it a little bit complicated. We will assume that the sender will never send the segment except if it knows for a fact that there is an empty buffer in the router. طب هو ده possible أصلا? Practically, is that possible? No, because we don't have visibility to the network. We'll assume hypothetically that this is possible. If that's possible, then we can have يعني lambda in will in fact lambda in dash will in fact be lambda in will in fact be lambda out. Because here the transport layer protocol will adjust itself to the buffer size of the router. If that's the case, then we will never have lost segments. صح? If we don't have lost segments, we will never have retransmission. If we don't have retransmission, lambda in dash equals to lambda n. What?
All of these are assumptions, right?
Assumptions. احنا we have assumptions which are not practical at all. Okay? We release them one by one. Okay? Until we reach, similar to what we have done for reliable data transfer. Think of yourself as a designer. We're trying to implement TCP now. Okay? We are going through the same thought process that the designers of TCP had to go through in order to come up with the final product. Okay? This is gradually the thought process they had to go through. So here, if the transport layer protocol was intelligent enough to guarantee that the buffer has empty size, then we will never have drop packet, we will never have retransmission, which means that lambda in dash equals to lambda in equals to lambda out. خلاص. So until we reach to capacity C over 2 or R over 2, in that case, خلاص, we will stop. And remember, lambda out can never get to greater than this, خالص. Okay, we will never have the case, because once we reach to C over 2, what will happen? The transport layer protocol will be stuck. خلاص, stuck. I don't have any buffer space. Give me buffer space, I can send. So after C over 2, it will stop. طيب. So this is that case, tries to explain that case. So if we have free buffer, we will send. So the segment will go from the application layer to the transport layer. If we have free buffer, then we send it, it reaches here. So this is the same scenario. We have the congestion scenario 2B. 2B here, packets may get dropped, which means that the transport layer protocol will not wait for the buffer to be empty. That's more practical, right? Because we don't know, okay? So due to full buffer, sometimes, the segment will get lost. Sender only resends if packet known to be lost. طب هو if the segment was lost, is it really lost because of congestion? Is it really lost because of congestion? That's an assumption, by the way, right? Here, the assumption here is that if the segment is lost, we know 100% that this is because of a router overflow. Is it really because of a router overflow? Not necessarily. What is the other scenario, لا, if خلاص everything is dead. The segment is routed, it's circulating. Okay? So it's not the fact that the router buffer is congested. There could be other reason, like the segment is actually sent in a wrong way, so it will not arrive to the receiver correctly by circulating in the network. Okay? But that's not 100% guarantee that the router has congestion. Okay? It could be. It's possible. But here, this will never happen. What we're trying to say here is that here, lambda in is the same, like lambda in dash is similar or greater than lambda in, okay? And if the segments were dropped, we will retransmit, but once they get to the router and the buffer is correct, they will always reach to the receiver. That's why here it's lambda out. The other case is that we have lambda out and lambda out dash back in. Okay? That the packets were dropped, but not because of a router overflow, because of other reasons. So in that case, you may end up with duplicate packets here, or duplicate segments come in. Okay? So we think that the router was in a situation of overflow, and we retransmitted the segment. That's fine. That's fine. We will retransmit the segment, and it will reach to the receiver. What is the other scenario? It reaches to the router, right? But the router does not have an overflow. But for me, I thought the router is in overflow. So I retransmitted the segment. What is the implication of this? I receive here a duplicate segments. But these two are effectively one, which means that here I have lambda out dash and lambda out. That scenario does not talk about this. Okay? There's no possibility that this might happen. If the segment is lost, it's lost 100% because of buffer overflow, sorry. Okay, which means that there is a state of congestion. Okay, but is that always true? No, that's not always true. Okay, so here بقى lambda out cannot be C/2 خالص إلا if يعني unless I have to increase lambda in very, 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 very large. So that's how it looks like. So there is no buffer, I will drop. And here you see when the rate is R/2 or the router capacity over 2, lambda out is a little bit lower than R/2. Why? Because lambda in has some retransmission, right? So what's reaching to the application on the other side is less than R/2 because some of these segments are being retransmitted. واضح? But if I increase more and more and more segments will be lost, but more segments will arrive. So eventually I can touch R/2 after some time by increasing. Before I was not able to increase because I only can send when the buffer is empty. But here I don't have this restriction, so I will keep pushing. And some of the segments will get lost, but some will arrive. Some will get lost, some will arrive. So if the rate increases a little bit more, I can reach to R/2, but I will never, ever go beyond that. We know this. Okay? So, case بقى C, the lost segments are not necessarily because of a router overflow. It could be because of a duplicate segments. So the receiver receives segments and some of them are duplicate. So in that case بقى, I have, so here I have timeout. I will send, even though the buffer was not full, but the timeout was premature. It's just that the segment here was delayed. It was not lost. That's one of the scenarios as well. Okay? So timeout was premature. I sent the segment again. And the result is these two segments are effectively one segment, but they will arrive as duplicate segments. So in that case, lambda out will never get to R/2. It will always be less because these duplicate packets will never allow the lambda out to reach R/2 by any means. So if you try to increase, you will have a duplicate segments and lambda out will always be less than R/2. Okay? So this is the cost of congestion. So you might actually feel like in all these scenarios, we have been able to push the router and reach close to the capacity of the router, even if there is congestion. Okay? But we can still get high throughput even if there is a state of congestion. Okay? Why is this? Because actually here, we're talking about only one router shared between two applications. In practice, we have a lot more complicated scenarios. So we'll talk about a scenario which is slightly more complicated, and we'll see the impact of this. The impact of this is actually very drastic. Yeah, this is what we talked about here. Lambda n dash, this lambda n dash can grow to what? Infinity. I need to push the router to the maximum. I can increase it essentially as I wish. I will cause a state of congestion. This assumes that the transport layer protocol will cause congestion. Okay? So lambda n can potentially increase to infinity, theoretically. But lambda out cannot reach infinity. Lambda out will be capped by R/2. But lambda in can go to infinity. صح? It's very important بقى. This is very, very important. Why? So that's the scenario. So this scenario بقى, we have multiple applications. Each two applications, they are communicating through two routers. Two routers, not one. Okay? So you have host A, host B, and assume this is host C, and assume this is host D. Okay? So host A, for example, is sending to host C through this session here. صح? Host D, for example, is sending to host B. And host B is sending to host D, and so on. So we'll see the interesting scenario here. So if I assume that host A is sending to host C, what we just studied so far tells me that host A, when it reaches here, the maximum that this traffic can get as an output is R over 2. صح? صح? That's what we studied so far. Assuming that this is fair. Okay? This R2, remember, this R2, this is the lambda out at this stage. This R over 2 is in fact here will become lambda in dash. So the situation now is that I have lambda in dash, which is maximized as R over 2, okay, is now competing with this session, the green one, coming from D going all the way to B, right? What is the maximum rate of this? The maximum rate of this. اللي هجاوب دي بقى يعني يبقى منتبه فاهم. ايه؟ لا I'm talking about lambda in here. So this is the end application at D, okay? Tries to send segments with increasing rate, okay? What is the maximum lambda in here?
Over 2.
Hmm? Huh?
Lambda plus retransmission.
Yeah. But يعني, to what extent I can increase lambda in here?
Maximum to R.
Why? Why? I can increase it over this. This is lambda in that is going to this router, right? So the output here is limited to R over 2, صح? But the input, oh? Let's go to this scenario. Because of this observation, remember you have very interesting scenario. You have a flow here which is capped by R over 2, competing with another flow which can potentially reach infinity. Okay? So lambda in is capped by R over 2, competing with another one that can go potentially to infinity. صح? Okay? What will happen بقى هنا? What do you think will happen?
If I keep sending,
Yes.
it will be unfair for D.
ماشي بس ايه اللي هيحصل؟ This one, will dominate and will fill the entire buffer. صح? Eventually. صح? مظبوط? So this one can get تقريبا to the capacity of the router, which is R بقى in that case, not. But what about the other one? Huh?
The other one, it will not manage to compete. Also.
ايوه بعدين يعني هيحصل لها ايه يعني؟
So bucket loss, congestion.
Yeah, what is the effective output rate? If one is dominating and filling the entire buffer.
Is it?
it will eventually go to zero. Okay? Type. This one will reach maximum to R. Okay? It will compete with this one. This one can go to infinity. What will happen here?
0.
Okay. Do you see the issue now? All of them, they will end up being zero. All of them. Can you imagine this scenario? Because all of them do not know how to do congestion control. So the message here is that if we're not responsible, we will all die. This is the big message here. If we're not responsible people living in a responsible society, we will all die. واضح المسج? This is a very critical issue. So in the previous, we were able to get to C over 2, R over 2. يعني, okay, until then الحياة حلوة, ما فيش مشكلة يعني. There is no drastic implication. But this scenario is a clear motivation that congestion control is not an option. It's not an option. So يعني transport layer protocol has to address congestion control. So this is effectively how it will look like. So if all of us working in this region, all of us are fine. Okay? They're assuming 2 routers, If all of us are working in this region, كلنا كويسين. If we start to increase and become irresponsible, all of us will die. All of us effectively will go to zero. Okay? This is a very drastic implication. One might ask a question. طب ما هو احنا we know that UDP does not perform congestion control, صح? Does not perform أصلا reliable data transfer. Does not perform anything. Okay? But we can live with unreliable data transfer. But what about congestion? ده معناها UDP can cause something like this? No. طب ازاي؟ UDP أصلا can UDP live without congestion control? Congestion control has to be done by someone. Okay? If it's not done by UDP, the application will do it. شفت بقى ازاي؟ Application will do it. But it has to be done. That's a clear motivation now. This is a clear motivation. Either we live responsibly or die. If UDP is not doing it, application will have to do it. That's why UDP is used very commonly in streaming applications. صح? It's used very commonly in streaming applications. Okay? But streaming application protocols, they have to perform congestion control. They don't provide reliable data transfer, but they have to address congestion control. It has to be done by someone, because congesting the highway, meaning everybody will suffer. So the cost of congestion when packet drop, any upstream transmission capacity used for that packet was wasted. يعني خلي دلوقتي احنا if we use the network irresponsibly, we are consuming the resources of the network, but effectively the output for all of us is zero. This is a very, very bad situation. So everything is wasted. يعني النتورك شغالة but nothing is coming up. This is a chaotic state. Okay? That's why congestion control has serious implications. So type, if we know that congestion control is not an option, how do we know that there is congestion? Okay? Type, TCP doesn't have visibility to the network. So there are 2 approaches. So there is, or 2 categories of congestion control techniques. There is end-to-end congestion control, or what we call a implicit congestion control. What that means is I don't have full visibility of the network, but I can get some implicit indication that there might be a congestion. That's what TCP does, typically. Okay? So we don't have any explicit feedback from the network. Because why do we avoid this? Why do we need to avoid explicit feedback from the network? Because it violates the layered stack. So this is some form of cross-control or cross-layer techniques, which violates the layered stack or the isolation of the layered stack. So we should try to avoid it whenever it's possible. Okay? ماشي. طيب خلينا نصلي نقف هنا. طيب. So we were talking about the end-to-end congestion control or the implicit congestion control. So in that case, we don't have any explicit or guaranteed indication from the network that there is a state of congestion. Congestion here means that the routers are congested with overflow buffer or buffer is filled. So there is no explicit feedback from the network, which makes more sense because the explicit feedback here would mean that there is a problem with the layer stack. There is some violation in the layer stack because transport layer protocol should not have direct access to the network layer protocols. Congestion here is inferred, معناها is actually assumed from the end system observed by loss or delay of segments. So we have these indications, either timeout or fast retransmission or 3 duplicate acts. These indicate to us that possibly there is a lost segment or a very delayed segment, right? Is that really an indication of congestion? Not necessarily. But for us, we will assume that there is a state of congestion. Okay, so it's an assumption. Okay? This is the approach taken by TCP. On the other side, there is network-assisted congestion control. Here, it's explicit. Here, there is an explicit feedback from the network. As we said, this is slightly an issue with the layered stack. That's why these types of explicit congestion notifications have been, not used in all types of congestion control techniques. So IP as a network layer protocol has an explicit congestion notification. If you remember in Network 1, people who studied Network 1 before, we have talked about the IP packet structure. In IP, there is a field called differentiated services. Does someone remember this? Vaguely, huh? There is a field called differentiated services as part of the IP header. This is actually divided into 2 fields. One refers to the packet priority. It's called differentiated service code point. يعني regardless, مش مشكلة. And there is like 3-bit field called explicit congestion notification. Okay? So IP is designed to actually provide explicit congestion notification. But it was never used in TCP or by TCP. So TCP chose to use end-to-end congestion control instead of using the explicit. Why? Because it tries to maintain that layer isolation. Okay? Otherwise, you have hundreds of routers. تخيل بقى how many explicit congestion notification you will receive from these routers. How do you deal with it? It becomes a big issue. So it's not easy. Okay? So it exists in IP, but TCP never uses it. Similarly, in other network layer protocols such as ATM and these are, again, network layer protocols. So I said application. Network layer protocols that have become totally obsolete. They lost ground completely to IP. So IP is the dominant network layer protocol on the internet. And ATM and other network layer protocols have completely vanished. Okay? So this explicit congestion notification happens when the router gets the buffer full, it sends explicit congestion notification. So we're sure that when we receive that there is a state of congestion, 100% that, there's no doubt. Okay, because the router only sends that when the buffer is full, when the router buffer is full. But there is, as we said, there is a big issue here related to the violation in the network layer stack, and also the scalability of this. If you have an end-to-end and you have hundreds of routers, you can potentially receive many of these explicit congestion notifications. So how do you deal with all of this? It makes the technique much more complicated. Okay? So how does بقى TCP perform congestion control? So now we know the principles, we know the impact of congestion. We know that there is very drastic implication if the transport layer protocol does not perform congestion. So the question is, how does TCP perform congestion control? The big message that we need to agree on here is that causing congestion control in the network is somewhat easy, can be easy, and we have studied some scenarios. But clearing the congestion is hard. Okay? Yeah, this is exactly similar to traffic jams on the highway. So you can easily have cars coming to the highway, but if there is a state of congestion, each car will have to wait for a potentially tens of minutes or hour before this traffic jam completely clears up. Okay? That's exactly what happens in the network. Causing the congestion on the router, on some of the routers on the internet, can be done easily. Why? Because you keep sending, and nothing is being lost. So what do you assume here is that everything is fine. So just keep sending. Increase lambda n. The router is not actually complaining, and the receiver is not complaining. So keep sending, right? But once there is a state of congestion, the router needs a long amount of time to clear up the buffer, right? To clear up the buffer. So that statement is very important, because that's the main theme of congestion control. You can cause congestion, but you have to be very careful. Once the congestion happens, you have to take a step back and say, okay, so I'll have to wait for a long period of time before this congestion clears up. So that's why TCP, that's exactly what it does. It keeps increasing lambda n, okay, until some tipping point here. If that tipping point happens, it's indicated by what? It could be indicated by timeout, could be indicated by duplicate acts, right? Okay? So if that happens, I will assume, and I have no other option, I will assume that there might be a state of congestion in the network. Okay? So at this tipping point, I have to drastically reduce the rate. Why? Because I have to give some time for the network to clear up. That's why the TCP has this sawtooth behavior. Sawtooth behavior. Yani it keeps increasing. Once there is a segment loss or duplicate acts, then it decreases exponentially, but not linearly. Okay? It reduces exponentially. And then it keeps increasing. Once there is a loss, so that it leaves longer amount of time for the router to clear up its buffer. واضحة كده؟ عشان كده we call it additive increase. So we increase by adding small increments of transmission, which essentially means that this is what we mentioned at the beginning. We start with stop and wait. We assume that the number of segments that we can send before we expect an acknowledgement is initially 1. Okay? And then we have to wait for an acknowledgement. If we receive acknowledgement, then, okay, so the network seems to be fine. It's like you are probing the network. You're probing the network. So the network gives you an acknowledgement, so it seems that everything is fine. Let me make it 2. Okay? Let me make it 3. Let me make it 4. This is what we refer to as additive increase. Once there is a timeout or 3 duplicate acts, no, we have to decrease drastically. So this is additive increase, multiplicative or exponential decrease. واضح كده؟ Clear? So our control parameter is what? Is what we call the control window, or we sometimes call it congestion window. So the congestion window, this is a parameter at the receiver. It's not in the header anymore. What's in the header is only the receiver window, which is used for flow control. This congestion window is a parameter that the sender controls. It's not in the header. واضح. يعني this has to be clear. Okay. So this control window starts, or congestion window starts with 1, which means that the sender will say, okay, so I will send only 1 segment and wait for acknowledgement. Receive the acknowledgement, then everything is fine. Okay, so let me send 2. Received 1 or 2 of the acknowledgement. Okay, so it seems fine. Let me send 3. Okay, and so on. This is called the south behavior. So, so the sender limits the transmission to last byte sent minus the last byte received, which is what we refer to as for flow control. But here we have also the congestion control. Okay, so the congestion control, the congestion window, it's actually the minimum of 2 things: the receiver window, okay, which is calculated based on this, اللي هو available buffer size at the receiver, and the congestion window at time t minus 1. This is at time t. Okay? So if the acknowledgement was received, the congestion window here can increment. Okay? So I can increment 1, and I keep incrementing until I touch the receiver window. The receiver window means that you're not filling the network, but you're filling the receiver. صح? Okay, so this simple control technique will take care of both congestion control and flow control. The receiver window is being communicated from the receiver in the header. Okay? Congestion window I can keep increasing as long as I'm receiving acknowledgement. Okay? So if the next congestion window is the minimum of these both parameters, then I'm fine. Okay? Type. The rate, let's talk about this rate. The rate is actually, how is this rate calculated? So this is the sender and this is the receiver. Assuming that initially I will send 1 segment and wait for the acknowledgement. And assume that here the maximum segment size is 1, which means that I send 1 segment and wait for the acknowledgement. Okay? So essentially, the rate is what? The rate is what I have sent over the total RTT time. This is the effective rate that I utilized the window or the channel of the network. It's the effective transmitted segment over the total rate. So this is the transmission time for one segment. Okay? And this is the total round trip time. This effectively refers to the transmission rate. So if I send two segments, this means that I have 2 times the transmission for one segment divided by RTT. If I make it 3, then it's 3. So effectively, it's the congestion window, which is the transmission time of all the segments in the window, divided by the total RTT time. This is the total effective rate of transmission from the sender side. Okay? So that's what this equation here refers to. The congestion window, which is the time required to transmit the entire window, the transmission time, divided by the total round trip time. So if I have 3 segments in the window, it's 3 times the transmission time for one segment. If I have 4, then it's 4 times the transmission time for one segment, and so on. So that's effectively the rate. Type. If I keep increasing like this, then one of 2 things might happen. There has to be a limit. So either we have timeout or 3 duplicate acts. So these are the 2 possible things that might happen. Either a timeout or 3 duplicate acts. So depending on these events, TCP might say, okay, so I will deal with them seamlessly. So both are, for me, both are similar. Both are similar. Which means that once I receive timeout or duplicate act, I will reduce the maximum segment size or the congestion window from, let's say, 20 packets to 1. And I start again. So I'll keep increasing. Once I get to the tipping point, I will drastically reduce the congestion window back sometimes to 1 or sometimes to half. Okay? Depending on this is what we will see. So as long as the congestion window for time t plus 1 or t equals to the receiver window, the minimum of the receiver window and the previous congestion window plus 1, then I'm fine. That's if there is no problem in the network, which means I do not have any event of timeout or 3 duplicate acts. Once I have a timeout or 3 duplicate acts, then this congestion window has to drop drastically, sometimes to 1 and sometimes to half. So there are TCP uses one of these. It uses by slow start. By slow start here we mean that this additive increase. Slow start, we start from 1. We start from a reduced state of stop and wait. The congestion window will be 1, which means I will send 1 segment and wait for the acknowledgement. Okay? If I receive the acknowledgement, I will make it 2, and then I will make it 3. This is called slow start. This is additive increase, multiplicative decrease. So if I reach to a tipping point, then I have to drastically reduce the congestion window back to sometimes 1. Okay? So the idea here is that TCP in some implementations, TCP uses multiple variations of congestion control. In some variations of this congestion control, it uses a differentiation between the 3 duplicate acts and the timeout. The timeout indicates drastic effect in the network. If I don't receive a single acknowledgement before the timeout expires, this indicates that things are seriously bad. But we said that there is 3 duplicate acts which sometimes refer to fast retransmission. صح? Fast retransmission here might not indicate that there is a serious impact in the network. It might indicate that there is only one segment that is delayed, but not necessarily completely lost. It may be lost, صح. But 3 duplicate acts indicates a less serious situation in the network. Okay? So some congestion control techniques differentiate between those two states. Okay? It differentiates between 3 duplicate acts and timeout. In some implementations, we say we will deal with them the same way. So for both cases, I will reduce the congestion window back to 1. I will start from scratch, and I will go again to the slow start state. And some of them, they say, no. If you receive a timeout event, go back to 1. If you receive 3 duplicate acts, go back to half. So there is a slight variation between the two. In assignment 3, you will be able to measure the performance of the different variations of congestion control techniques for TCP. Okay? So this is the last slide. خلاص ما عارف عملت ابص في الساعة. So when connection begins, increase the rate exponentially until first loss happens. So 1, I will start with 1, as we said. I will start with 1. I receive the acknowledgement, RTT. So I will increment to 2. Received 1 acknowledgement. Why 1 acknowledgement? Why not 2? It's cumulative. مش مشكلة. خلاص. It's cumulative. One acknowledgement is enough. صح؟ يعني هنا it's less than 500 milliseconds, so it's fine. 1 acknowledgement can supersede the other one. But this is an indication that everything was received successfully. So I will make it A. Here, slow start doubles the window. The slow start here doubles the window. So I will make it always double the previous one. So instead of sending 2, I will send 4. Okay? If I receive 4 or even 1 cumulative acknowledgement and everything is fine, so the 4 becomes 8 and so on. So why would double the window? Because if everything is fine, this indicates that the network is fine. So if you make it 1, 2, 3, 4, this means that you're not really utilizing the channel efficiently at all. Okay? So you may actually try to create some variation and see if you make it increment like this, what will be the performance of TCP? It will be drastically inefficient. So there is a compromise between utilizing the channel efficiently and causing congestion state. Okay? So you need to have a trade-off between the two. So TCP uses this increase. You always double the window until there is an issue of congestion or there is a loss of a segment. In that case, you will drop again from the congestion window of 1, maybe, or half. Okay, we'll see the difference between the two and we'll be able to measure the performance. Okay? So the summary is that initial rate is slow, but ramps up quickly. Okay, so that's the idea. And once there is an event, we'll see the slight difference between the 3 duplicate acts and the timeout. We'll see it next time, inshallah. Okay? Any questions so far? تمام? Okay?